right. So good morning, everybody. My name is Tim Beechie. I am from the Northwest Fisheries Science Center with NOAA Fisheries. We're in Seattle, and I'm in the watershed program, and a lot of our work focuses on analyzing what kinds of restoration might be needed or might be most cost effective for salmon populations. And today I'm going to talk about one project that we've worked on in the Chehalis Basin using life cycle models to help understand which kinds of actions might be prioritized over others, and also using a process-based habitat change analysis to set that up and to drive the changes in the model. It's not advancing. Let's see. There we go. So process-based restoration, just a quick reminder, one slide. So the goal of process-based restoration is to reestablish processes that sustain river and floodplain ecosystems. River and floodplain is important here. I'm going to focus, even though we did a lot of different analyses of different kinds of habitat factors that could change salmon populations in the Chehalis, I'm going to focus on the floodplain ones today because those turn out to be particularly important for at least a couple of the species and also for providing some resilience to climate change. Some key features of process-based restoration, which of course stage 0 very much is, it's not static. So once you get the processes in place, they maintain the river ecosystem, or at least the physical parts of the river ecosystem on their own. So it's self-sustaining. You shouldn't have to go back in and do maintenance and things like that. And a key feature also is that it allows natural biodiversity to emerge. So one issue that comes up is in a lot of places we have multiple species listed or of concern, and it's difficult to prioritize across species. So one thing that process-based restoration does is allow each location to support the species that it's capable of supporting. So the process-based analysis, you've probably all seen this before. This is a pretty old concept that we've used for a long time. So landscape processes drive habitat conditions and drives biological response. And those can all be affected by humans, so we can change either the processes that drive things. For example, we can change the condition of the riparian zone, and that changes wood recruitment and shade, which changes habitat conditions, and then cascades down to a biological response. Or we can affect habitat conditions directly by working in the channel, or even biota directly through harvest or hatcheries or other practices like that. In this case, we're going to focus on two questions. The first question being, how have habitats changed and what does that mean to the fish? In this case, we're talking about salmon populations. And then the second question, what are the root causes of the habitat change? So in this first one, we're looking at the lower linkage, the link between habitat conditions and the fish response. And then, then the upper one is, what are the root causes of habitat change? So what is it that actually makes the habitat the way it is, and what do we need to fix in order to allow it to come back? So what do we need to do that? So we need to identify the root causes of ecosystem change. So we typically work with at least these 5 key factors: sediment supply, flow regime, floodplain, riparian, and connectivity between habitats. So you can add other ones to this as well, but most of the functions that we're interested in fall into one of these 5 categories. And then once we've done that, we need to assess the changes in habitat type. So we do an inventory of the current habitat that's out there, both amount and condition, and then we do an estimate of what was out there historically as well. And then we run those through the life cycle model to see which types of habitat change are most important for different species. And one thing you'll notice here is that there's only one habitat change. You know, that the habitat's the same for all species, they just use it differently. So in that middle diagram, this one here, this is the % change in each of the habitats, and going from left to right, it's delta, main stem, floodplain, tributary, and beaver ponds. And you know, main stem hasn't changed very much. The other ones have changed a fair amount. And then what that means to fish depends on their life history. So Chinook, for example, in the middle, you see you're mostly responding to delta and main stem habitat change, whereas coho respond to delta, floodplain, and beaver pond habitat change. So the life cycle model concept. So this is a diagram for coho, and you see the gray box on the left is where we start. So spawners, we have spawners returning to the basin. They deposit eggs, and then that goes through the incubation stage, the egg to fry stage. You have emergent fry and a colonization stage, and then you have a summer rearing stage here. I'm thinking you can see my arrow, and then a winter rearing stage, and then we have a delta bay stage, and then into the ocean for different rearing years in the ocean. And there's a maturation rate, this B parameter, which is a percentage of fish that come back from each age class. In coho, it's very simple. There's only jacks that come back in addition to age 3s, whereas for Chinook and steelhead, it's a lot more complicated. But what we're trying to do here is we have this life cycle model, and we know that we have parameters, capacity and survival parameters driving each life stage, and we want to know how different habitat factors affect those. So barriers, for example, can affect how many spawners get to a place and how many eggs are deposited. Fine sediment can affect this incubation survival. Shade can affect summer rearing through its effect on temperature. Floodplain habitat can be a big factor for winter rearing for coho salmon. Beaver ponds the same, also a winter rearing habitat for the most part. And then wood can affect multiple life stages. And I'll go into the different stages and parameters that each of these affect a little bit later, but this is just to give you the concept of what we're trying to analyze. So what we want to know is for each of these factors in the colored lettering, how much difference do they make and how much restoration potential is there? So we set up the model like this. We have the life cycle model at the bottom. So if you're thinking of the coho one I just showed you, that's the bottom 2 rows. And then the top row is the drivers. So these are the things that we can change in the model. So we can turn each of those dials. For example, we can change how many migration barriers there are and where they are, or we can change the road density or the amount of wood. And those factors all drive habitat conditions. So those are all linked through various functional relationships that change either a spawning or a rearing area or a quality attribute like fine sediment or temperature. And then those translate into the life cycle model inputs. So again, we need a capacity and a productivity for each life stage. And so those are determined by the habitat conditions in each location. And then once that goes into the life cycle model, at the bottom, we get salmon population abundance and productivity out of the model. So again, to do this, we need to assess the driver and habitat changes. So what we need to start with is quantification of the natural potential and the current conditions so that we can calculate change. So for each factor, for example, riparian functions, we want to look at how big are the trees that are out there now, what kind are they, how much shade do we have, how much wood recruitment do we have, and then compare that to a natural reference condition. And that gives us an estimate of the change from the historical to the current. And so we can quantify that natural potential condition in a few different ways. One is if we have historical data, we can use that. If we don't have historical data, we can use contemporary reference sites. These are often hard to find, but if you can find places that are relatively undisturbed or least disturbed, you can often get some pretty good information from those about what conditions you might expect. And if you don't have either reference sites or historical data, you can use models to estimate what a historical habitat condition was like. And then current conditions, we're usually just using field data or remote sensing data. So again, focusing on the large river and the floodplain habitats, I'll go through an example of how we do this historical and current assessment for channel pattern for the large rivers and the main floodplains in the Chehalis. So we have several different channel patterns that we could have out there. Straight on the left, which has often very little floodplain, but when it does have a floodplain, there's still a fairly straight channel without a lot of migration. A meandering channel, it's typically very low gradient, very high sinuosity, and has some pond and marsh habitats associated with it, but not usually a lot of side channel. There's a few. We have island braided, which has usually a lower sinuosity, but still sinuous, but lots of side channels and islands. And then braided channel, which is similar to island braided, except these are unvegetated gravel bars separating the channel. So this channel is moving around so much that the vegetation usually doesn't establish within the main channel. And so what we want to have is for the relevant types, which in the Chehalis Basin are these two in the middle, meandering and anabranching, some reference estimate for how much side channel should be out there, how much main channel length there should be, how much pond and oxbow and marsh habitat there should be. So I'll go through an example of how we went through that. So for example, we looked at 2 studies that showed what is the sinuosity, typical sinuosity of reference sites for meandering and island braided channels. And the bars are from a study by Brian Collins and Dave Montgomery, and the points are from one of our studies back in 2006 in Western Washington. And what we found was that sinuosities in both studies showed are quite a bit higher for meandering channels, 1.5 to 1.6 being a mean value. And then island braided channels are quite a bit straighter, so only about 1.2. So we use this value when we're looking at channels that have been straightened and we don't have a way, we don't have a historical map that shows us how much sinuosity was there historically. We use these reference values to estimate how much channel we think might have been there before and compare that to the length that's there now. The reference side channel length, this is again from a study that we did in Western Washington, showing braided and island braided on the left having a fair amount of side channel length, often around 2 times the amount of the main stem in side channel length, whereas meandering, as I pointed out in the photo, doesn't typically have a lot of side channel, and straight channels have very little side channel. And then where we did have historical information in this case, this is a map of the Chehalis Basin. So the yellow outline is the Chehalis emptying into Grays Harbor here. So this is the mouth of the river. And all of these blue polygons are historical marshes and ponds that we got from the General Land Office surveys in the late 1800s. And you can see that there are certain locations in the basin, particularly down here in the eastern part, the southeastern part, where there was a lot of marsh out there historically. And so these were wide valley bottoms, relatively smallish channels with a lot of marsh, a lot of channels, a lot of ponds. So probably very much like what you would think a typical stage 0 channel would look like in this basin. We have a couple other pockets of habitats that are marsh and pond up here, and then most of the rest of them are along the main stem rivers, as you would expect. So what do we get from all of that? So here's just an example, again, for the Chehalis, showing in the green bars what we had out there historically, and in the dark blue bars what we have there that's currently functioning at a relatively natural level. And what you see is that we've lost more than 90% of the functioning marshes and ponds. Some of them, this light blue, there's quite a few that are still out there, but either fish can't get to them anymore, or they have no riparian vegetation or some other modification that makes them less functional for salmon. And ponds also very, very few left in natural conditions. And then I don't have a graph for it, but when we estimated the historical side channel length that was out there and compared that to what we have left today, we lost about 91% of that. So quite a bit of loss of floodplain habitat in this basin. And these losses vary spatially. So this is just a map of change, and I won't go through all of them, but let's just look at the floodplain one down in the lower right corner. And you can see, these dark areas where we've lost a lot. These are those areas on the aerial map image that I showed with a lot of blue polygons. So this is where we had a lot historically. Almost all of that has been drained for agriculture and development at this point. And then there's this pocket up here that also had the little cluster of ponds and marshes that have mostly been lost or degraded in some way. And then the rest of it, as you would expect, is along this main river channel or some of the larger tributaries. So then we want to translate those into habitat conditions. And so the life stage parameters for the life cycle models, we have capacity and productivity that we need for each life stage. And then each habitat change can affect multiple life stages. For example, as I showed in the life cycle diagram, wood can affect either the spawning life stage or the summer rearing stage or the winter rearing stage. So for fish use of main channel habitats, one of the things that we're doing, obviously, for each habitat type is estimating its capacity to support juvenile fish. Here's a picture in the lower right showing some main channel habitat types. So we have bar edges, so these are very shallow, low slope bars. And then we have bank edges, which are steeper edges, usually have a lot more cover. And then we have these backwater or alcove habitats that can be off to the side. And what we see is that fish densities, they definitely choose certain habitat types over others. So both coho and Chinook tend to favor backwaters and bank edge over everything else. And modified banks with riprap tend to be about half, tend to have about half the capacity as natural bank edges. Bars are relatively little used by either of the species. So floodplain habitats, we had, as I said earlier, we had marshes, which are on the left there. Marshes in this particular area are dry in the summertime, so fish density for coho is 0. This is just a coho example. Ponds are wet year-round, so we have fish in there year-round at relatively high densities, both summer and winter. Side channels, much lower density, especially in the winter. There's a big drop in the winter where these side channels like this one here are not used as much in the wintertime. Sloughs behave very much like ponds, so they get the same, or get this is the density of a large pond. This is a small pond of the 1.8. And then survival is also different among these, especially for the winter. So survival for coho in the winter goes from about 0.35, a little more than double, to 0.78 when you switch from a main channel to a floodplain habitat or a pond. And then Chinook also nearly double, going from 0.29 to 0.53. So not only a lot of capacity change when we lose or add these habitats, but also a big survival difference. So these can affect multiple life stage parameters, as I said, and when we're talking about floodplain or stage 0, some of the main things that we're talking about are channel length, the bank condition, and floodplain habitat areas. You can affect some of these other ones too, obviously, but I'll just focus on these for now. And you see that something like either the channel length change or the floodplain change affect both summer and rearing capacity and productivity, as you saw just from those densities and survivals that I showed you, and the same with winter rearing capacity and winter rearing productivity. And this is for coho and steelhead. If we look at Chinook, which in this basin have a different life history, they all go out as sub-yearlings. So we're only looking at affecting sub-yearling capacity and productivity, and not much effect on pre-spawn productivity in this case. So spring Chinook here are holding through the summer, and they are affected by temperature quite a bit. We could actually have an X here because in our model, the floodplain connectivity does affect the stream temperature as well. So once we have those, we develop habitat scenarios. So the first one we call the diagnostic scenario. So we look at what would happen if we could go back to the historical condition for any one of those drivers or all of them together. And then we can also create future scenarios to evaluate climate change effects and restoration alternatives. So diagnostic scenarios look like this. So we have a scenario where we first run it with all current conditions, and then we want to see the effect of each of these drivers separately. So we take current conditions and we take all the barriers out. And then we see what the population response is. And then for the next one, we put the barriers back in and we set the historical fine sediment level and see what that does. And then we put the fine sediment back to current, and then we change the wood, and we just step through these one at a time. And then at the end, we run all historical conditions together. And the results look like this. This is, again, the example for the Chehalis Basin. And if we start with coho, so floodplain and beaver ponds are the green and purple bars on the right. The brown bar is wood in the middle. And those are the most important factors for coho salmon. You see that things like barriers and shade and large river habitat don't really have that much effect on coho salmon in this particular location. But floodplain habitat and beaver ponds tend to have a really high response. Spring Chinook also has a pretty high response for floodplain potential. But they also have a big effect from either shade or fine sediment, and that's largely because these fish are going out so young. They're not spending much time in fresh water, and the shade has a big effect on temperature for the adult holding period, and then fine sediment obviously is an incubation survival factor. And then fall Chinook are affected by fewer parameters in steelhead as well. They do have some response to floodplain habitat, but not as much as the others because of their life history. It's just not as floodplain connected as, for example, coho or spring Chinook. And so not only do we want to know what kinds of things can make the most difference, so if we're setting up a strategy at the basin scale, this result would give us an idea of what we need to restore for each of the species. But we also want to know something about where each of those can be restored. And so we can map each of these in sub areas or sub basin units and see what the change is. And so if we just focus on, let's just look at coho, for example. So the top row is absolute abundance change. The bottom row is percent change in abundance from current condition. And this is all for floodplain reconnection. So if we look at the spatial distribution, let's look at percent change. We see that certain basins, like this is the Cascades subbasin and the main stem, have a fairly high potential to increase spawner abundance through floodplain connectivity, whereas some areas with relatively small streams and less coho potential overall, because they're steeper and have very little floodplain, there's not much potential. So this can also give us an idea where to focus the effort in addition to what kind of effort we need to apply. So then we can look at the climate change and restoration scenarios. So climate change, in this case, we're running a model that has fully stochastic peak flow, low flow, and stream temperature. So each of these varies from year to year. And we've developed them with an empirical data set to give us the year-to-year variation pattern, and each one is correlated with the other. So we do an analysis that creates a simulated stochasticity where all of those are correlated with each other. And then in addition to that, we create different restoration scenarios. So we can do lots of different combinations with this model. We can do either very tailored ones where we set up a spreadsheet that has every subbasin listed and the different actions that you're going to take in each subbasin and the intensity of the action in each subbasin, and the model can read that in and give you a very detailed or a response to a very detailed strategy if you want to go that way. Or in this case, I'm just running some fairly simple ones for an example. So we can do a no action scenario. We just go forward with climate change and don't do any restoration. What do we expect populations to do? And then we can target either the 4 most important actions or the 5 most important actions or all actions at different intensities. So in this example, we're starting off with actions at 25% of their historical potential. So what that means is in the model, let's say that the floodplain response was 40%, or there's a potential of 40% increase in population abundance if we could reconnect all the floodplain habitat. When we apply an intensity of 25%, that just means we're going to go up 10% out of that 40. We're going to take a quarter of it. And we can do that for any action. In this case, it'll be the top 4, the top 5, and then all actions. So here's an example. There's a few things to see in this figure. So these are the different species listed from left to right, or coho, fall chinook, spring chinook, and steelhead. And one thing that's pretty obvious right away is that coho and fall chinook are relatively less sensitive to climate change in the no action scenario, the red bar, than are spring chinook and steelhead. Spring chinook in particular are very sensitive, and a lot of that is because this population is such low abundance right now. It's around 1,000 fish. So there's not much left to work with, and if you throw climate change at it, it doesn't have a lot of resilience. And then there also have varying responses to the restoration actions. So if you look at the top 4 or top 5 at 25% for coho and fall chinook, by 2080, you can still be at roughly current abundance. You wouldn't have improved much, but you would have prevented not an insignificant decline for each of those species. Whereas if you did the 25% effort for spring chinook and steelhead, you would still have a pretty significant decline by the 2080s, and you have to put in a lot more effort, either 50% or in some cases up to 75%, to get a substantial spring chinook or steelhead population to persist through the 2080s, at least under the climate change assumptions that we have here. And there's different things that we can do about that. So just doing one temperature example to compare a no action scenario, a shade scenario, a floodplain scenario, and a combined scenario. So this is just looking at the full restoration potential. If we could restore the shade to natural condition or the floodplain to natural condition, or both shade and floodplain to natural condition, what's the response? So this is not looking at all restoration actions, but just these ones that target shade. And what we see is that, you know, not surprisingly, I can't see the labels on the right on mine because it's covered by, let's see if I can move. Yeah, there, get the bar out of the way. So spring Chinook on the top, again, by late century, so a pretty significant decline. There's a big drop if we don't do anything. We can prevent some of that drop by doing either shade or floodplain restoration, or a more significant part of that drop by doing both actions together. And again, whereas coho, they're not as sensitive, so they're not dropping as much to begin with. And if we do shade restoration, we get some benefit for coho. We get very little with floodplain reconnection for coho, and that's largely a function of where these fish are. So spring Chinook are generally in the larger rivers, and so doing the floodplain restoration has more of a benefit for them because it's cooling the temperature where shade has less effect. So these rivers are wide, and growing the trees doesn't make as much difference as it does on the small streams. So that's where the coho are, so they're responding more to that small stream than they are to the floodplain habitat. So those are some of the kinds of things that we can do with the life cycle model to understand what floodplain restoration benefits might be for different species. It's not advancing again. There we go. So just last slide. So summary. So the life cycle model approach, what we're using it for is to help target more cost-effective restoration. So as I pointed out in the diagnostic scenarios, we want to know what to do and where to do it. And so that's how we're running this model, and it seems to be pretty effective at doing that. And then also just to point out that floodplain restoration has multiple benefits as they're modeled in this life cycle approach. So they increase marsh and pond rearing areas. You can increase side channel spawning and rearing area, increase overwinter survival and summer survival for that matter. You can help decrease stream temperature by reconnecting hyporheic flow, and you can attenuate increasing flood flows in the future. So hopefully that's a good setup for some of the talks that will come later, just to give you a perspective on how floodplain restoration in general fits in the context of a river basin for multiple species. It looks like we're on time, so I think we have time for questions if there are any. I saw one flash by, but I don't see the whole. Let's see if I can find the. There we are.
So Tim, can you see the chat box, or do you want me to read them to you?
I have it up now. Yeah. So it looks like I see Rob, Paul.
Paul was asking about if it's possible to see life history change for Chinook.
To see a life history change. So yes and no. So the part of the way this model works is you're putting in the life history variants. So for example, we have a fry migrant type and a sub-yearling migrant type. This particular basin does not have a yearling migrant type, but we're going to be modeling that in some other basins. And so we enter those, and so we know that all those life stages are there. What it can change is the proportions of those. So if you run the model that, for example, increases capacity for the sub-yearlings to stay in the basin, then you increase the proportion of those fish that have higher survival, and in the end, you get not only more fish, but you get a greater percentage of those of one life history type over another. So it's kind of a yes and no, that it really changes proportions of life history types more than. I mean, it doesn't create a life history type if you haven't put it in, I guess is what I'm trying to say. You have to enter all of those at the beginning. And then might some rear longer if those refugia habitats were available through the winter? Yes, yeah. So that that is definitely true of coho and steelhead, that if you have better rearing habitat, you could have them staying in there longer or surviving better. The model won't really, the model won't change the length of time. It's set on life stages. So winter is a step in the model, winter rearing. So it won't, the only thing that can happen is if fish die in the summer or if they're leaving early as Chinook fry migrants, then yeah, you would have less of those there in the wintertime or late in the summer, depending on the species.
And it looks like Lee also asks, has this predictive type of modeling been done for resident trout?
That's a good question. I know it's been done for Atlantic salmon. Maybe George knows if it's been done for resident trout. I can't think of any off the top of my head, but it doesn't seem like it would be hard.
Hi, everyone. This is George. Not that I know of, but we could certainly look into it and see if we can find any examples.
Are these data and model predictions based on unaltered and natural flow regimes? So they are based on current flow regime for the peak flow component and the low flow component. So when we run the stochastic model, we're putting in a current or a recent time series. I think we usually start around 1990 and come up as recently as we can get. So we try to do a 30-year time series to create that year-to-year variation for each flow. They're, see, I'm trying to, I mean, they're natural except where the dams are. That's the only one, I think, and there's two relatively small dams in this basin. So for the most part, I would say yes, they're natural. Although, I mean, there's some effect of forestry, logging, and maybe some effect of urbanization, although urbanization is very small in this basin. But then when we run them forward, we add the climate change projections for increasing peak flow and decreasing low flow. In this particular basin, that's the pattern. It doesn't have to be increasing peaks or decreasing lows, but that's what's projected to happen in the Chehalis Basin. And so when we run those forward, we definitely have altered flow regimes into the future.
Are there any other questions for Tim?
Yeah, Tim, this is Brian. The draining of the marshes probably had a profound effect on hydrology, maybe late season flows as much as any part of it. Is that in the model?
It is not. So we're limited by what we have data for, and that's one thing that we would like to try to do, and we may try that in Puget Sound because I know they're interested in the effect of beaver ponds as well as floodplain connectivity. We know that at least conceptually there should be an increase in summer low flow with floodplain reconnection and with increase in beaver ponds, and that's been documented in a number of places. So we know it's there. We just didn't have enough data to figure out what the, if we reconnect 50% of floodplain, how much does the flow? Couldn't figure out how to make a number out of that, as opposed to just an understanding that it would change.
Mm-hmm. Thanks.
Then Chris asked the question, would it be reasonable to run this type of model on conceptual project alternatives? Tim?
So generally, yes, although not for individual projects probably, because each individual project is so small, it makes essentially no difference for a population. So you can definitely say, and you can even do what ifs, like you could say if floodplain reconnection increased peak flow or increased low flow by X amount, how much difference would that make? So you can put in any set of restoration alternatives that you can quantify the habitat response for. So the model is really flexible that way. You can, I mean, it's just R code, and if you say, oh, you didn't think about, I don't know, I can't think of a good example off the top of my head, but if there's something we left out that you wanted to put in, if you have the data to create the functional relationships, it's very easy to put a new function in there. And share some links. Yes, we can definitely share links. We have all the data up on the website, the underlying data. I don't think we have the code up there yet, but we can certainly share code.
Tim, would you want to type your email in the chat box, either when
Sure.
George is talking or sometime soon, and then people can also direct some questions to you following the talk as well. And another plug, in case those participants haven't received those 7 papers, Tim did have 2 papers in that stack. So be sure to let me know if you haven't received a link, and I'll email it out with the 7 reading material papers that we had. It looks like Kate also, I don't know if you read the chat on hers. Your model talks about fine sediment as a negative impact, but many of our systems are fine sediment limited, and we need those for island formation, change, habitat needs, lamprey. Have you considered looking at the positive effects of fine sediment in your model?
Yeah, it's a good question. We have not. So this is one of those perfect cases of where the same factor affects species differently. So lamprey, for example, need the fine sediment, as this one says, whereas coho spawning gravel or Chinook spawning gravel does not need to have the fine sediment. And so the same thing is going to affect species according to their life history needs. We have not done that in this particular case, but as with any of these habitat factors, if you have data and relationships to do that, it's not that complicated to add new factors.
Okay, thank you, Tim, for that. And I apologize, I didn't have your intro slide up beforehand, but I was supposed to mention that you hold a bachelor degree in geology, a master's degree in fisheries, and a PhD in forest hydrology, all from the University of Washington in Seattle. So Tim did leave his email address in the chat box if anyone has any follow-up questions, and then we'll also try to have time for a question and answer session towards the end of the day.